But conformism, mainstream conformism is not a new phenomenon. I remember speaking, when I was a postdoc at Princeton, I remember speaking with Martin Schwarzschild. And he told me that in the 50s, most astronomers were working on binary stars, which is by now obsolete. And they were debating about it, and conferences were filled up with talks that sounded just like each other. Everyone was talking about binary stars. And he said it's not very different from today. And he meant back in the 80s when people were working on something else that was very fashionable. Only the topic of the day changed. So this is not a new phenomenon that most people prefer not to take risks. There are only a few that are willing to take risks. But I think that it is much more prevalent today. And the reason is peer pressure, job security, and large groups. So we have to be careful. For the benefit of the field, we need to encourage creativity. And the history of astronomy teaches us modesty. We should not be dogmatic. The kind of feedback I get from young people is that they say, you know, we know that there is dark matter, we know that there is a cosmological constant, and they are very dogmatic. They are very much opposed to thinking outside the box, outside the simulation box. But let me give a few examples where this was actually proven not to be a good approach. The sun does not move around the Earth. I mean, we see the sun moving in the sky. It's sort of obvious that it's moving around us. The church advocated that. They killed people that thought otherwise. They killed people. But it's the wrong idea. The sun is not moving around the Earth. Philosophers and Einstein thought that the universe existed forever. It makes much more sense. How come there was a point in time when everything started? What created this point in time? What was the origin of the Big Bang? That doesn't make any sense. It makes much more sense that the universe existed forever. Turned out to be the wrong idea. There is evidence for the Big Bang. We don't know what happened before that. This is a local example. If you ask Harvey Tannenbaum, he will tell you the story. Back in the early 60s, they were trying to promote an X-ray mission, a satellite that will probe the sky in X-rays. And NASA was opposed to it. They said, there's not much to expect out there. Not much X-ray mission. And if there is a mission, why would it be interesting? That was NASA back then. We should not be dogmatic. We know that the X-ray sky is very rich. And I expect gravitational wave astronomy to open a completely new frontier once it observes the sky in gravitational waves. And there are good reasons for us not to be dogmatic, especially young people should not be dogmatic. And there are good reasons for that. The universe is composed mostly of ingredients whose nature we do not understand. We should admit that. We get paid to explore the universe, and we don't know what it's made of, right? The dark matter or the dark energy. And an illustration of this is in this remark that was made by Simon White at the Sackler conference. He was the speaker that was supposed to conclude the Sackler conference on the Milky Way galaxy that took place here in May this year, just a few months ago. And he said in his summary talk, we have been trying to simulate the formation of a galaxy like the Milky Way for 20 years in lambda CDM. And we have not succeeded. Okay? So if you think about it, there are all these semi-analytic models, all kinds of excuses for why the galaxy mass function does not look like the Hello mass function, all kinds of prescriptions to explain the disparity. But it's also possible that the theory of galaxy formation is a reincarnation of the Ptolemaic theory of epicycles, that we keep inventing epicycles. And perhaps our conception of dark matter or dark energy is wrong. That's quite possible until we understand how galaxies form. And here is a numerical simulation, well, not numerical, but a simulation that was done in 1598 to demonstrate the viability of the Ptolemaic theory of epicycles. The Earth is in the center, and the planets move around it. It's much more natural to assume that the Earth is at the center of everything. Here's another illustration that confirms the results of this one. And here is a semi-analytic model, whereby the planet is actually executing these epicycles. And there was a very fancy math that accommodated this semi-analytic model. So we should not be dogmatic, because the universe is composed of constituents that we don't fully understand. Moreover, the distribution of matter has not been mapped through most of the universe. And by most, I mean 99.9% of the observable co-moving volume of the universe was not mapped. The distribution of matter in it was not mapped as of yet. All of the parameters that I showed in the first slide, where I showed the constraints on cosmological parameters, these were derived based on the microwave background anisotropies, which come from a surface around us, which has a very little volume, and from the SDSS survey that probed out to a redshift of 0.3. And that constitutes about 0.1% of the co-moving volume of the observable universe. So who knows? Maybe something else is lurking out there with low probability. Here is a map that unfortunately looks very similar to the Ptolemaic map, but it's actually correct. We are sitting here, and the Big Bang was 13.7 billion years ago, so that's the distance of our horizon, 13.7 billion light years. That's as much as we can observe. So for all the observers in the audience, we can actually observe only this volume. And in fact, not precisely all of this volume. There is this sliver here, which is the time when the universe was opaque. So we can't use telescopes to look through it. We can see all the way out to a redshift of 1100. But that makes up almost all the volume. And so far, we looked out to a redshift of 0.3, which makes up 10 to the minus 3 of the co-moving volume of the universe. So what we would like to do is map the distribution of matter throughout the rest. And one way to do that is using the 21 centimeter line that will probe, for example, the epoch of reionization, a fair chunk of this volume. You have to realize that the volume scales as the distance of a shell squared times its width. So the farther the distance is, the co-moving distance is, the more volume you probe. And of course, SDSS3 will use the Lyman forest to map the distribution of matter closer to us. So the bottom line is we haven't observed most of the universe. We should not be dogmatic. Especially young people should not be dogmatic. And the reason I address this to young people is because they're more capable of taking the roads that were not taken by others. Part of this is that they lack the baggage of unwarranted prejudice. Another way to say it is that they don't know the risks. That's why the army takes young people to wars, right? They're willing to die. Older people are not willing to die so easily. They have families. So the same is true about science. Think about the frontiers. The young people are charging ahead. They don't think about the risks. And that, well, they haven't thought decades ago. Now they are thinking too much about the risks. Because they lack baggage, and they have a flat Bayesian prior about the roads that may lead to discoveries. And they find things in places that other people do not find. So if you look at the work of the most distinguished physicists, like Einstein or others, the important work was done at an early stage in their career. Moreover, senior researchers are distracted by administrative and fundraising concerns. And because the funding agencies prefer projects with predictable results, they actually they direct senior people in directions that are conservative. So senior people prefer to have a conservative profile with predictable goals, just like the funding agencies encourage them to have. And that's unfortunate, because it leaves a very narrow window for young people to actually be creative. That's the time when there are postdocs. Afterwards, they have to worry about things which are esoteric to the actual doing of science. It would have been nice if the funding agencies would allocate a fraction of their funds to out of the mainstream projects. That would solve the problem. So the reaction I get from young people when I say that, and this is a slide that I added after my talk at the banquet, the reaction is, yes, you can say that, because you have tenure. So you can say, you can encourage us to take risks. You can take risks because you have tenure. Well, I wanted to demonstrate my point by mentioning a few examples that demonstrate that I personally haven't changed. I was advocating the same philosophy all along. So let me give you a few examples. When I was a postdoc, I worked with Andy Gould on microlensing as a method to detect planets. That was out of the mainstream. People didn't think much about microlensing back then. Now it's actually one of the main missions of WFIRST. During the tenure process, when I arrived here, I worked on first galaxies and reionization. There was very little interest in it. In 1993, when I came here, there were only maybe 2 or 3 people around the globe that were interested in reading my papers. Now, this year, there are 2 books related to this frontier. One book is a book that I wrote, summarizing how much progress we made over the past 2 decades on this frontier. And the second book is the Decadal Report, which listed the formation of the first stars and galaxies as its second most important question to address for the next decade in astronomy and astrophysics. Okay. It also listed the cosmic dawn as one of the 3 themes of scientific inquiry for the next decade. And specifically, you see here the first stars, the first galaxies, and black holes. So coming from the fringes, where there are only a few people interested in it, to making it a main research frontier for the community of astronomy and astrophysics. I was not involved in the Decadal Report. None of my students were involved in this context, I don't think. And, well, John can correct me. We can look at the list. But the point is that what is regarded the periphery at some point in time can become mainstream 2 decades later. So that's an example. And that's what I worked on during the tenure process here. And after getting tenure, there is another example. I, for example, wrote a paper on measuring the cosmic acceleration or deceleration in real time. That was in 1998, using the Lyman alpha forest. Turns out that Sandage proposed using galaxies, although that's not very practical. And now people are working on either the AstroComb or Codex on the European Extremely Large Telescope as a method for detecting the acceleration or deceleration of the universe in real time, waiting 10 years and seeing that, for example, the redshifts of the Lyman alpha forest changed a little bit. So I don't think it has to do with whether you have tenure or not tenure. It has to do with your attitude, and you can do it at any step in your career. But I have to mention a disclaimer about taking risks. Most ideas fail, or you find that they were explored by other people. The fraction of my research time that is allocated to innovative ideas is far greater than the fraction of my papers that are innovative. There is a lot of wasted time when you explore new territories, because many of the ideas do not lead anywhere. You have to realize that. The efficiency is much less than you would expect from a predictable goal. Therefore, failure and waste of time are a common outcome of venture capital investments, of research time. But if they are successful, they may bring highly profitable returns. So you gauge the profit versus the risk. And the other thing that you have to realize is that new ideas are accompanied by loneliness. And you go to conferences, you see lots of people getting very nurturing feedback if they work on a project that is a variation on a theme, simply because there are many